Okay, so we are, you've seen, excuse me, peanut stuck in my throat. You've seen chemical reactions before in our life through chemistry so far. You have seen things written out, this plus this gives you this. But we are starting to analyze what that means and how to balance them and how to read them in a little bit more detail than what you've seen so far. So a chemical reaction or a chemical equation is it looks like a math formula. There are some groups of substances that you combine in some way, and then they do something. They respond to each other's presence. They pass electrons back and forth, or they pass atoms back and forth, and you wind up with something else. So you have certain things that react together, and we write those on the left-hand side of the equation. And we say that those are reactants. They are things that we are reacting together, okay? Baking soda plus vinegar. You put those together in a beaker and they bubble and foam because of all the carbon dioxide that they release. So the baking soda and the vinegar are reactants. They go together in some container and stuff happens. So the reactants are what you mix, and then what you produce at the end are the products. So the reactants react to produce products. And the products are the things on the right side of the little arrow sign. Now, if it were math, we would say equals. And the equal sign means that what's over on the right is the exact same thing as what's over on the left. 2 plus 2 equals 4. If you have two things and two things in the same, place, you have 4 things. And 4 is the same as 2 and 2 more. We don't use an equal sign in chemistry because it's not the same thing. Baking soda plus vinegar is not the same thing as carbon dioxide and salt, okay? And so we don't say an equal sign because they are not the same. Something has changed. Something has happened. And so instead of using an equal sign, we use the little arrow that says that these things become this thing. And that arrow, when you're reading a chemical equation, you say yields. It yields. It does this. It produces this. Okay. So an example of a chemical reaction. Here I have methane, CH4, or if you didn't know that this was called methane, what would that name be? How would you name CH4? Not chlorine. C is carbon. Carbon tetrahydride, yes. So methane or carbon tetrahydride plus oxygen. These are the reactants. Yields water, or what was the name for water again? Or dihydrogen monoxide. And carbon dioxide. So these are the products. This is what we have made. These are the things that are produced. These are the things that I mix together. And so they are the reactants. And then this little thing, not an equal sign, it's yield. So methane and oxygen yield water and carbon dioxide. That's an example of a chemical equation. And we're going to get to, in a little bit, analyzing the kinds of chemical equations that there are. There are several basic categories of reaction. And you're going to look at what category does this fit into. But for right now, just identify reactant, product, and yields. Okay. The other thing you need to know is that reactions need to be balanced. If you have a certain number of carbon atoms or hydrogen atoms in the reactants, you need to have that same number of carbon and hydrogen atoms in the products, because remember, matter is neither created nor destroyed. It just changes forms. So if I have 1 carbon and 4 hydrogens on the left in the reactants, I should be able to find 1 carbon and 4 hydrogens on the right. So let's look at that. Do I have 1 carbon and 4 hydrogens on the right? No. Uh-oh. What happened? Well, I have 1 carbon. Yes, I have 1 carbon. But here I have 4 hydrogens. Here I only have 2 hydrogens. I need to balance this equation. I need to play with multiplying molecules until I have the same thing on both sides. So what I'm going to do is I'm going to add coefficients, numbers that serve as multipliers, and I'm going to balance the equation. So if I put a 2 in front of the water molecule here, then what I've said is that this reaction of methane produces not one molecule of water, but it actually makes 2 molecules of water. And that 2 in front multiplies everything that follows it. So I have here 4 hydrogens, and here I have 4 hydrogens. Here I have 1 carbon, here I have 1 carbon. So the methane is balanced, okay? In the original equation, I had 2 oxygens, and here I had 1, 2, 3. Well, 3 and 2 are not the same. But when I multiplied my water molecule here by 2, I also gave myself 1 more oxygen. So now I have 1, 2, 3, 4 oxygens, and originally over here only 2. So I've got to add another coefficient in front of the oxygen so that I have 2 molecules of oxygen, and I have a total of 4 atoms of oxygen on the left in the reactants, and 4 atoms of oxygen on the right in the products. You guys see what I did there? When you write a chemical equation, it has to be a balanced chemical equation. So again, this just goes through it. 1 carbon, 4 hydrogens on both sides, and 4 oxygens on both sides. Does anybody not see how you use the coefficient? Does that confuse anybody? Okay, cool. So, many reactions can happen in both directions. And so in the methane plus oxygen gives you water and carbon dioxide, the last example. If you take natural gas and you have it in the presence of oxygen, and you give it a little spark, it burns. And methane gas burning in the presence of oxygen gives you water vapor and carbon dioxide. And you can't just take the water vapor and carbon dioxide and turn them back into oxygen and methane. It doesn't happen. And so that we use the yield sign, because it only goes one way. The reactants turn into products. The products don't throw it in reverse and turn back into reactants. But some chemical equations can. Some chemical reactions go one direction and then can reverse and go backwards. So you could take products and mix them together under the right circumstances and get reactants again. You can get something to unwind itself, right? And so in that situation, we don't use the yield sign because the yield says it only goes this direction. We use instead an equilibrium symbol, which has an arrow going in both directions, saying that this thing, these reactants or this reactant, can turn into these products. And these products can react with each other and go back this direction and turn back into this thing. So in the example here, I have a kind of sugar, fructose, okay? And fructose is a natural sugar found in mostly fruit, but other places as well. And so fructose, in the presence of an enzyme, aldolase, is broken down into 2 molecules, dihydroxycetone phosphate and glyceraldehyde 3-phosphate. This big 6-carbon molecule is cut in half into 2 3-carbon molecules, basically is what happens. So one big thing gets cut in half. But your body can also take these 2 3-carbon molecules and stick them together and make fructose again. It can go both ways. It can go towards the products, or it can go towards the reactants. And so to put just a one-directional arrow there would be not entirely the whole story. That would mean that the fructose only ever gets broken into 2 3-carbon molecules. But in fact, these can also go that way. So we use that equilibrium sign with an arrow going both directions and says this can go this way or it can go that way. Okay, so it's a two-way road instead of a one-way road. But it's still not an equal sign. We still don't use an equal sign because equal would mean that this is the same thing as that. No, not true. But the process can go either direction. You guys understand that idea? Questions? Shanice, you good? Pretty good? Yeah. Okay. All right. Take a moment, write that down. I'm going to stop talking here for a second. Okay, so chemical reactions. In real life, you're going to be taking two materials that you can manipulate in some way and putting them together. And a reaction will happen. When the reaction happens, sometimes what's made, some of the products, will be gases. And unless you've got an apparatus set up that's going to catch the gas is just going to bubble out of your solution and leave. And it'll go into the air that you're breathing. And if it's bad gas, then you do it outside. But the gas that's made bubbles out of solution. And so we want to show in our chemical equation that we made this gas, but it's not there anymore. Like it left. It took its ball and went home. And so we'll draw a little upward arrow next to a gaseous product to show that it's a gas and it's leaving now. It's going bye-bye. Okay? Also, sometimes you'll have liquid substances that you mix together and a solid is formed. Something in the liquid reacts with something in the other liquid, and the product that they make is a solid, and it comes out of solution. So liquid plus liquid makes chunky. Okay, if you've ever accidentally mixed milk and a strong acid, like if you've ever put lemon juice and creamer in your tea. Has anybody ever made that mistake? Lemon juice and creamer in your tea? Okay, I did. And what happens is the lemon juice reacts with the milk and it curdles, and you wind up with like brown cottage cheese in your cup instead of tea, right? So, yeah, when you have that, it's a liquid and a liquid, but their reaction produces a solid. That's called a precipitate, and oftentimes we'll draw a little downward arrow next to the precipitate to show that, hey, these other things were liquids. But when I made the reaction happen, I got a solid out of it, and the solid settled out of solution. It wound up at the bottom of my Okay? So some precipitates are drawn with a down arrow. And then oftentimes we will put the state of matter in parentheses after the molecule or the compound that we're talking about, to say that at this particular time, this substance is a solid, liquid, or gas. Okay, just to let people know when they're reading it. So let me show you some examples. Well, you can't see the arrows. Oh, Sal, there's supposed to be an arrow there. Okay, well, if I had made chlorine gas, there should be an upward arrow. Sad. Upward arrow would show that the chlorine gas leaves. The calcium carbonate is a solid precipitate, and then there should be a downward arrow that says this goes away. And then AQ means aqueous. That means that the hydrochloric acid is dissolved in water. It's a liquid right now. So it's dissolved hydrochloric acid. I thought I had another example. Anyway, I don't. Take a moment and write that down. Okay, so there are different kinds of chemical reactions. There are just a couple of broad categories. One of them is a synthesis reaction. Synthesis means to take things and put them together. A synthesizer, an old 80s instrument that takes sound files and combines them to something that sounds cool when you play it. Synthesis means to stick things together, okay? So a synthesized reaction or a synthesis reaction is when I have two things and I combine them together and I wind up with one thing at the end. So A plus B is AB, right? Two things together. And so this would be like taking hydrogen gas and combining it with oxygen gas and then sparking it and letting it burn. And then you wind up with water vapor, and then you cool it down and you can have a glass of water. Okay? So that's hydrogen gas plus oxygen gas gives you water. That would be an example of a synthesis reaction. And so two things that are separate, two reactants yielding one product. Okay? A decomposition reaction is the exact opposite. Decomposition means to have one thing and turn it into multiple things. So when you die, you are one thing. Congratulations. And then, you know, a couple of years later, you're a whole lot of stuff. And so one thing turned into lots of things. That would be like the fructose that I showed you a couple of slides back, where there was one molecule of fructose. But then that one molecule of fructose was able to be broken into 2 3-carbon chains, right? Or you could look at the opposite of the water example that I gave you and say, if you take water and you pass it through a strong electric field, then the electrons from the electric field are able to get in there and interrupt the bonds, and you will get a little bubble stream of hydrogen gas coming off of one electrode and a little bubble stream of oxygen gas coming off of the other, and you'll break water into the 2 elements that it's made of. That's a decomposition reaction. Synthesis and decomposition are opposites. And then there's some replacement reactions, where you have some atom that's by itself, and it comes in and jumps into a molecule and replaces something that used to be joined to that. So A and B are bound together into a molecule, and then along comes C, and A dumps B and is now hanging out with C, right? So we can get into like social analogies and say A and B are dating, right? And then C just moves into town, and A's like, wow, C is so much cuter than B, and dumps B for C.
Oh,
Okay?
great.
Yeah, yeah.
Oh,
So
great.
that's called a single replacement reaction, because in a single replacement reaction, you have one thing that replaces something else in that chemical reaction. So here, if you were to have, let's say, methane, CH4, and you have a container of methane, and then you bubble some more reactive gas through there, like chlorine gas. The chlorine will kick out some of the hydrogen out of the methane, and instead of being CH4, it would be like CH2Cl2, and it would kick out some of the hydrogen, because the chlorine is more reactive and bonds to the carbon more readily than the hydrogen did. Okay. Tracking with this? Yes, you were.
I'm applying that to school.
Oh, you and I are friends, but then I'm not really. I'm going to go be friends with this person. Is that what you're saying?
Yeah.
Oh. Okay.
It's basically everyone in school.
Yeah, I know. So that's a single replacement reaction. The other last one would be a double replacement reaction, where you have a molecule composed of, 2 different things, and then you react it with another molecule composed of 2 different things, and the one molecule and the other molecule trade partners. So A used to be with B, but now A is with D. And C used to be with D, but now C is with B. So again, in the social analogy, you go on a double date with another couple, and at dinner you decide that the other couple has a better partner than you do. And so you're both like, hey, could I just switch? And the other people are like, yeah, we're good with that. So by the time the double date is over, you've got a new girlfriend or boyfriend, and so is the other person. So everybody's still happy. Everybody's still happy. You just decided that you're over that person. Okay? So that's a double replacement reaction. These reactions frequently happen between acids and bases. So hydrogen and chlorine, hydrochloric acid, reacts with sodium hydroxide, which is a base. If you put hydrochloric acid and sodium hydroxide together, the hydrogen from the hydrochloric acid actually winds up hanging out with the hydroxide from the sodium hydroxide, and you get H2O, you get water. And then the chlorine from the hydrochloric acid winds up hanging out with the sodium from the sodium hydroxide, and you get salt. So you take a very strong acid that you should not drink, and you take a very strong base that you should not drink. Either of those could kill you. But if you mix them together in the right relationship so that they react perfectly on a one-to-one relationship, you wind up with salt water, which you could drink and would taste nasty but would not kill you. You'd have to pee a lot afterwards, right? And so this is a double replacement reaction where two things both trade, and you wind up with entirely different substances at the end. Okay? So I have a little video to show you of this. I'm going to stop recording for a moment.